Welcome to this tutorial on Salome-Meca or Code-Aster, and our topic today is parametric study using astk interface, and we'll take up for illustrating the parametric study. We'll take up a slope stability analysis example. And now first, what is meant by parametric study here? Parametric study here means that in a simulation we need to use various parameters. Say for example, if I analyze the deformation or stresses in some structural member, say I am doing elastic analysis, my input parameters will be, say, modulus of elasticity, Poisson's ratio, then loads, then boundary conditions. Okay, and then if the sum of the parameter or one of the parameter changes, say modulus of elasticity changes, and we need to say study how the deflection of a beam changes with the modulus of elasticity, or how it changes with the say moment of inertia of the section. So in that case, that parameter, say moment of inertia, I will keep varying in the simulation, and I will see what is the deflection, say how the deflection varies with the variation of say moment of inertia of a beam section. So those kind of studies are called parametric studies, and these are very important for design purpose. It is also called sensitivity analysis. Say for example, in a geotechnical problem, you know that the geotechnical parameters are determined by some laboratory or in situ tests, and there are some inherent errors in the method of determining those parameters. And if my value of a parameter during the design that is assumed in a design, if it changes afterwards, then how the system will behave. Those kind of studies are called sensitivity studies. That means how much sensitive the result is to the change of some particular parameter. So those kind of studies are called parametric studies. And there is a interface called astk, which you can invoke either from Code-Aster or from Salome-Meca interface. And in astk, it becomes pretty easy to conduct parametric studies, and our basic objective is to show how we can use astk for doing the parametric study. And to illustrate this, we are taking a slope stability analysis example. We'll try to find out what is the factor of safety of a particular slope. Okay. So for that purpose, I have selected this slope. It is a homogeneous slope having the slope material and a base layer, and the dimensions of the slopes are shown here. This width is 20 meter, the slope length is also 20 meter, and this toe portion is also of 20 meter length, and the height of the slope is 10 meter, and the depth of the base layer is 5 meter, and the unit weight of the soil is 20 kilonewton per meter cube, cohesion is 15 kilopascal, and phi is 20 degree. And this slope is analyzed in this reference, programming the finite element method by Smith, Griffith and Margetts. It's a very good book, and we will analyze the same thing using Salome-Meca. And for that purpose, you all know that when we go for slope stability analysis in finite element method, we basically use strength reduction method. And I think many of you are familiar with strength reduction method. For those who are not very accustomed or familiar to this method, what we do is, in strength reduction method, what we do is, we gradually reduce the strength parameters of the soil, namely the shear strength parameters, say C and phi, by some factor. This factor is called strength reduction factor. In short, we are writing as SRF. And what we do, we analyze the slope for different values of these reduced C and reduced phi, where the reduced C is defined as the C by SRF, strength reduction factor, and reduced phi is such that tan of reduced phi must be equal to tan phi by the SRF, so that phi reduced is defined as tan inverse of tan phi by SRF. And first we select a few probable values of SRF, which should include the probable value of the factor of safety, and then we calculate the reduced C and reduced phi for each of these SRF values, okay, and then we analyze the slope with those reduced C and reduced phi value, okay. So there will be as many analyses as the number of SRFs, and finally, if my SRF is very close to the actual factor of safety of the slope, then what happens? The deformations or strains increases indefinitely and the slope becomes unstable, okay. Earlier generation of finite element programs, when those were used, it was assumed that whenever the nonlinear analysis does not converge, then the whatever SRF that leads to that non-convergence condition is taken as factor of safety. But now, due to increased computer power and better and better softwares, convergence will be, in most of the cases, convergence will be achieved, and particularly say Salome-Meca or Code-Aster, convergence can be achieved for almost any material nonlinearity by using elastic stiffness matrix. Of course, the number of iterations increases, number of Newtonian iteration for every load step increases to high value in that case. But anyway, our analysis converges, and therefore to indicate failure, to study failure, what we can do is we can note down the maximum deformation within the slope for each SRF value, and when the deflection increases drastically, then we reach that factor of safety. So the SRF which causes to increase the displacement or strain drastically, that value of SRF is taken as the required factor of safety. So that's how we do our strength reduction method analysis, analyzing slope stability by using strength reduction method, okay. So next, let us see our So this is our slope. This is the mesh I have already created. And going back to this slope geometry, let me tell you which I missed earlier. Let us name these different portion of the slope for grouping. This I am calling as top line, this as slope line, and this as toe line. And this is my left support, this is my horizontal support or H support, and this is my right support. Okay, and my actual value of the shear strength parameters and unit weights are these. Gamma is 20 kilonewton per meter cube, cohesion is 15 kilopascal, and phi is 20 degree. Okay. Now, if I use the strength reduction factors, then what I can find out the various values of reduced C and phi by applying the equations just now we have discussed, and I have done it in some small program. And you can see that these are my SRF values. Okay, these are my SRF values 1, 1.2, 1.4 and 1.6. For SRF 1, that means it is the original C and phi value will be there. So cohesion is 15,000 Pascal and phi is 20 degree. And psi, which is the dilatancy angle for Mohr Coulomb constitutive model, is taken as 5 degree. Okay. And when SRF is 1.2, I have divided this original cohesion by 1.2 to get 12,500 Pascal. Similarly, phi becomes 16.873 degree, and so on. So these values are already calculated: the reduced cohesion, reduced phi, and reduced psi. All right. Now we need to use these values for analyzing the slope. These values of C and phi for analyzing the slope. So this is my mesh. This is a quadratic mesh I have taken. It is fine enough mesh. Okay, and these are my various groups. Say for example, if I show you the base layer, these are my group of nodes. Let me show the group of faces. Say this is my base layer. Okay, and this is my top layer. Similarly, my support, horizontal support is this, horizontal support is this. Okay, then right support is this white line, then left support is this line. I cannot see it because the axis is covering it anyway. So that's how my various groups are defined already in the mesh. All right, and mesh file is stored here. All right. Now the analysis can also be done by using Aster-Study as usual by invoking the Aster-Study. All right, Aster-Study here. Okay, but in that case I will have to do many such analysis, and it will be time consuming. So instead what we can do is we can use astk. To invoke astk, what we do, we click here in Tools menu, then Plugins, we have Code-Aster, then Run astk. If you select this, then we get there is some information. Okay, it says that the local host is not defined, so the present machine is taken as local machine. You say OK, then this is my screen for astk. Okay, astk is a easy interface to set up the analysis by telling the system which one should be our COM file, which one should be our mesh file, etc., etc. Okay. Now, before using astk, let us see first the COM file first. Okay, this is my COM file, which was obtained, which was generated by Aster-Study for some value of cohesion and psi and phi. Okay, cohesion, then dilation angle and angle of internal friction, which will be used for defining the material. All right. Now, when we use directly Aster-Study, what happens is, in the more Coulomb parameters in definition of material, defi-material, what we would have got angle dilation equal to say 5 degree if my SRF is 1. Cohesion is 15,000, phi equal to 20. So those values would have been written. Now I have modified this COM file in terms of writing these values in terms of some variables. All right. I am calling the dilation angle as psi, cohesion as capital C, and phi as pi. Okay. And I am giving the value of C, psi, and phi initially as defined in this COM file. All right. You can even put this any value, C equal to 0, psi equal to 0, phi equal to 0 also when I use parametric studies in using astk. Okay. So this is a usual COM file for analyzing the slope for self weight. Because the more Coulomb material is used, we are using static nonlinear analysis. Okay, I have divided. I have defined some list of times. Okay, list of real and list of time as usual. And here in the defilist inst, what we have done is, excuse me, I have used the automatic time step cutting in case of non-convergence. All right. So these things you must be familiar with, these methods. If you are not familiar, you can see my earlier videos discussing nonlinear analysis of a geotechnical slope or slope material using Salome-Meca. And then we have used a ramp function for applying the weight. And these are my boundary conditions. This is my self weight, which is gravity. And I have defined the rho of the material already. Rho is this, because gamma divided by 9.81 will give me rho in kg per meter cube. Okay. And then what we have done here, as usual, we have applied the self weight and the boundary condition. And in the nonlinear static analysis, stat non-line, the first part, 25% of the total weight is applied assuming the material as elastic. So comportment is elastic here. And the remaining part, the behavior or material behavior is taken as more Coulomb. Okay. And the more Coulomb parameters we have already defined in the material definition. Angle of dilation is psi, angle of cohesion is c, angle of internal friction is phi, and their values are written here for FOS equal to 1, SRF equal to 1. And then as usual we are doing the analysis. We are calculating the stresses and strains by calc-champ, and we are writing the results in MED file as well as in tabular form for displacements. Okay, this is necessary so that we can draw the curve that we have just now discussed. If you remember, this curve, in order to draw this curve, I will need the displacement to plot displacement versus SRF. So I need to read the displacement, and therefore I am writing the displacement here, okay, in a file, and I am writing the displacement at the final instant of the analysis. All right, final instant of the analysis, which is the 60th step. So nume orderi is 60. I can also say time instant, inst equal to say 20. My inst to a maximum value of time was 20. So anyone you can do, and we are noting down the maximum value and minimum value. So value max is V, yes, and value minimum is yes, and the unit is 80. And the result RMED file has a unit of 2. Okay, so these unit numbers are important to be noted down. Okay, to set up the analysis in our ASTK. Okay, and as usual, I think our MED file, mesh file is unit is 20. So let us note down those values here. Okay, let us note down that units, logical units, my MED file, was 20, then RMED file, result file in MED format is 2, and my data file, tabular file, text file, resu file was 80. Let me verify once again. Yes, MED file is 2 and data file is 80. So fine, we have noted them. This notation is important, this noting down is important, so that we don't make any mistake in setting up the ASTK, setting up the analysis using ASTK. Okay, so now let us go for then ASTK again. Well, before going to ASTK, what we need to do for parametric studies, we need to make a text file whose extension is DISTR, distrib, that means distribution. In Code-Aster jargon, the parametric study is called distribution study. So we need to open a file, text file. You can give any name to this text file, but the extension must be DISTR. I have already created this file to save time, and the file format is like this. What we need to do is we need to write valet equal to, then one bracket, and it is to be ended in another bracket, okay? And then we write the factor keyword underscore f, then the various combinations of C, phi and psi for different SRF values are listed here. You remember for the first case my cohesion was 15,000, phi was 20 degree, psi is 5, okay? So that's why in this first case I am writing C equal to 15,000, phi equal to 20, psi equal to 5. And remember, these C, pi and psi were my variables used in the COM file to define the soil material. Is not it? You see this soil material. Dilation angle I am calling it as psi, cohesion as capital C, and angle of internal friction as capital phi. So I must use those notations, those values, whatever are the values, psi, C and title case phi, okay? Those must be used in giving the values. Those variables must be used. That is important. And for SRF equal to 1.2, my cohesion value was 12,500, pi was 16.873, and psi was 4.1699. So I am writing those values in the second case. Okay? So like this, we are writing all these values in this format. Valet equal to one bracket, then next bracket should be below few lines, and within these we write these lines. All right. Now, while setting up this study in astk, we will be using this distrib file. I have named it as param.distr. So this file must be available in the directory. So in the directory, what I have to have the made file for the mesh. I have to have the com file where I have defined the material in terms of the variables whose values are given in the distrib file. Okay. And also, since it is a parametric study, there will be number of results. To store those number of results, I must have a directory already created. You can use any name for this directory. Okay, I have called it all studies, and right now it is empty. All right. Now what I will do, I will invoke my astk from here, tools, plugins, Code-Aster, run astk. So I get this astk interface. The first thing I need to do is I need to tell the base path. That means the directory where I have all the files necessary. For that, I can use this thing. There will be a warning which says that in the file names or folder names there cannot be any blank. If there is blank, then instead of a blank you can use underscores. Okay, So in my home directory, it has got this file. It is giving me some warning. I say OK. Now it is opening my home directory, and let me go to the required directory. Every time it is giving me the warning. So this is my directory, then parametric studies, then this is my study. Okay, so this directory will be my base part. I will say OK. So this is my base part. All right, now what I will have to do, I'll have to tell the system which is the com file, which is the made file, etc., etc. Okay, for that I will create a new file by using this this icon here. When I touch this icon, you can see that at the bottom it is written. You can see at this place, when I touch this, insert a new entry in the list. Okay, so I click this. First the com file type is coming. If you click here, all different types of file which can be used in ASTK are coming in the drop down menu. So first is my com file. So I will come here, and then I'll open that directory, and my stage1.com was my file. So I am saying OK. Okay, this is some bug where it has come down and it has gone up. I can delete this line like this. Now again I will open a new entry. Then first I will give the made file. Okay, so I should use mmade. Okay, mmade file type. Then I click here, left click here, then go to this, and I give the made. This is my made file name. Okay, and this is my again this has come unnecessarily, so let me remove it. So this is my logical unit 20. Let me check if I have correct logical unit. I noted it down. So made file is 20. We have seen here made file is 20. Made file unit is 20. So my ASTK thing is OK. So this is 20 is OK. And you see this is a data file. This both com file and made file will be used as data in the analysis. So this D column is ticked automatically. This D means data, this R means record. Okay, that means where I will write the results. So again I need the message file. Okay, so the type is MEWS, so mess. So I will give some name. It is not existing, so I will use dots slash. That means in this directory I will use, say, parametric dot MEWS. This is my name of mesh file, and this its unit by default is 6, and it is a record file where the system will write the things, write the message. So this R is automatically clicked. All right, then I need to have my RMed file, right? RMed file, and I will write this as a res02 .rmed. This is again record. By default RMed file has a unit of 80, but in our case it is 2. So let me make it to manually. All right, so this is my armed file. Then I need to have this data file where maximum deflection will be written. So I again enter a new thing, then this will be data file, that file, okay, that file, or I can also use resu, and this is my say depl dot resu, or depl dot out will also do. Okay, let me make it that file, and let me make the type as that, and let me call it depl dot out. Okay, and my unit is 80, so let me manually correct it to 80, and this is again record. Okay, and then I need to have one more entry for the distrib file, right? So my type of file is distr, and here I will open this dist file, param.distr. okay, and its unit is 0 by default. Okay, again this bug has come into picture, so let me remove it, and it is a data file again, it is already existing, so this part is ticked. And then to write all the results in the directory, I need to have one more directory definition, and in French directory is called reportier. The actual pronunciation I have forgotten. I think it is repertoire, something like that. So I will call this as since I have already opened the directory, I will open this and I will point to this all studies directory, and this is the repe. Again its unit is 0. Okay, so this one has come unnecessarily, so let me remove it. So these are my files necessary to be set up, and you see this repe is both data and record is clicked because this repe is already there, but I should remove this this data tick. I should untick it so that it writes there. All right, now I can save all this setup as it is asking me save the current environment. Yes, it will be in the same base directory. I will call it say parametric. I will write the date July say 02 2021 dot astk. The file extension is astk. Okay, so okay, once I save it, what I can do is if I want to repeat the analysis, or the analysis I had some problem, I had to fix something, then again to repeat the setup, I need not write all these things. I can just open, say what I will do, just let me show you. Since I have saved, I can close it really quick. Yes, Now what I can do is I can just open my file from the directory, appropriate directory. Once again, like earlier case, parametric study, mesh. Now this is my astk file. When I say OK, all these things are automatically coming. All right. Now what I will do is, since it is a huge study, I will give more memory. I have 32 GB, so I will give 16 GB, and I will give time as, because it is quadratic mesh, so the number of degree of freedom will be quite high, so therefore I give, say, 3 hours 15 minutes. And then I can use various versions available of Code-Aster. I have from Salome-Meca, I have 14.4. I have 14.4 installed as Code-Aster in my system. You may not have it. You may have only this one if you have installed only Salome-Meca, not Code-Aster. And I have also installed 14.6 version of Code-Aster, so I will use this 14.6. And I will write here interactive follow-up. This means when I run this study, I will get one terminal where the progress I can monitor. It will keep on writing the message file, basically. Okay. So my study is set up. These things were not set up initially. All right. Let me save it again, because now these are correct. And then I have to, if I am doing a parametric studies, I should go for options. Then there is a distrib option. I should say yes. Distrib, yes, okay. All right. Then let me save it. Save this environment again. Okay. Now I will start running the study. Run. It is confirming me that it is distribution is yes. Following options have been defined. Confirm. I say yes. Now my study has started. All right. And I will have 4 analyses. It will take quite a long time. So let me pause the video and I'll come back once these results are out. Okay. Welcome back to this tutorial on parametric studies using astk or Code-Aster. And we were analyzing a slope for its stability using strength reduction method. And finally our results are out. And you see this is one screenshot of the astk interactive terminal where these different calculations are carried on, and this part shows the time. I think I should slightly enlarge it for your benefit. These are the times necessary in seconds for every calculation, and you can see that these calculations take quite a bit of time. And as we approach, as our strength reduction factor approaches towards the factor of safety, actual factor of safety, this time necessary increases because the convergence becomes more and more slower, and therefore many a times in slope stability analysis we may have to repeat the analysis with some new selected factor of safeties or SRFs so that convergence is achieved. And Also, we may need to adjust the analysis settings like maximum number of global iteration, and then automatic step downing of time. Okay, so those features of Code-Aster needs to be adjusted for a particular problem so that we get the convergence near the actual factor of safety. However, what my experience says is that although Salome-Meca or other softwares, the new generation softwares are very, very sophisticated in terms of algorithms for convergence, still when we exceed the factor of safety, we do not achieve convergence for very large number of iterations and also for very long time duration of analysis. For example, in this slope, I took an SRF of 1.7 and the convergence was not possible, and therefore what I did, I took a few additional factor of safeties or SRFs like 1.6 and 1.65, and after adjusting the global number of Newtonian iteration to about 12,000, which is very large, I achieved the convergence in this SRF of 1.65. all right. So depending on the value of SRF and how close it is to the failure, we may need to increase the number of Newtonian iteration, and we may also adjust the parameters related to automatic time step cutting, okay, in the analysis. So these are some of the adjustment necessary for slope stability analysis. So once our results are out, what we should do is we can go to the folder which we created during this setting up of our study, and these are different calculations for each set of parameters, and we gave originally 7 calculations, and they are serially named as calculation 1, calculation 2, calculation 3, etc. However, during the actual execution in the astk, they need not be serially taken up by the system. It may happen that calculation 6 will be done first, then it may pick up calculation 2 to be executed next. Okay, so that seriality is controlled by system, not by the user. However, once you get the results, what we should do is we should always check whether our results are fine or not, whether the analysis has been successfully over or not. And for that purpose, whenever you open one of the calculation folders, you will get some files, whatever you have set up. This was our data file for recording the maximum and minimum displacements, and this was our armed file, okay, and this was my message file, and this is my command file. So we should always first open the message file, and we should go to the bottom and see whether the exit code is 0 or not. So this is exit code is 0, therefore analysis was fine. And in the beginning you see the values of C, psi and phi used here. So these were my original unreduced values, so this is for SRF equal to 1, and that's why we have got it in calculation 1. So accordingly you know that which calculation relates to which SRF value, okay. and we can see the result in data format. And I have asked to write down the mesh file. So this is the mesh file in Aster format, and then finally the values of displacement at the final instant of calculation, that is 20-second, has been recorded here. Maximum dx, maximum dy, minimum dx, minimum dy. Okay, and also the nodes where they have occurred, these values were obtained, is also reported here. Okay, so these results for all the SRF will be used to draw the plot of displacement, maximum displacement versus SRF at a later time. Okay. Now let us see the results of our analysis. I told you that we had recorded the maximum displacements, nodal displacements, maximum nodal displacements and minimum nodal displacements in a data file for each of the analysis, and by picking up those maximum displacements for different calculations, different values of SRF, this is our plot of maximum displacement versus SRF. Here we are plotting the x displacement. I write it as dx in terms of Code-Aster terminology. So this is the plot of dx, maximum dx with SRF, and we see that beyond the SRF of 1.6, the displacement suddenly increases to a very large value, and therefore we can take the factor of safety, actual factor of safety of the system as 1.6. Okay, so that's how we can find out the factor of safety, by plotting displacement versus SRF value. So we can note it down now that this is my factor of safety. Okay, and this FOS is equal to 1.6. So this is the result of our slope stability analysis. All right, and let us compare our results with the result of Smith et al. That we have already discussed earlier, and they have got also a similar curve of maximum displacement versus SRF, and they stopped analyzing at SRF of 1.6, and they found that the SRF is somewhat maybe at about 1.55 or so. Okay, as per this calculation. And the same slope was also analyzed by Bishop and Morgenstern in their publication in 1960, and they got approximately 1.58, which is marked here in Griffith. This is as per Griffith's solution. Okay, Smith et al. Solution. So this is our factor of safety as per the present simulation, and this is the factor of safety given by Smith et al. In their book. And we see that our factor of safety is pretty close to Bishop and Morgenstern. Okay, Morgenstern. Now let us see the deformation, how the deformation has taken place. This is the slope displacement at the verge of failure as per Smith et al. And this is our simulation at SRF of 1.6, and you see this shadow is the undeformed geometry of the slope, and this is the deformed geometry, and we are showing here the displacement dx, and this clearly shows that this is the failure surface, generated failure surface. Okay, and the geometry of failure surface is very similar to Smith et al.'s analysis. And here also this portion has come out of the original geometry, and here also it has come out. This difference is because of basically the difference of scale or enlargement. And they have plotted the vector diagram of the displacement, and when we see the kind of deformation that is taking place from the warped geometry, this is the deformed geometry, we see that the deformation pattern is very similar. All right, and this was our result for our additional simulation of the slope at an SRF of 1.65, and this is the deformation pattern in with this SRF. So actually it has already failed. So this has shown a huge deformation even up to the base layer of the slope. Okay, so that's how we have seen that our analysis is pretty well compared along with the Smith et al.'s solution. However, we have seen that displacement at SRF of 1.6 obtained by Smith et al. Is nearly 38 centimeter, and in our case at 1.65 it is slightly more than 40 mm. This is around 38 mm. I am sorry, okay, because this is 40 mm. So we see that our slope is slightly more steeper than their slope. That may be because of various reasons. What I can see is that we have adopted the value of gamma, c and phi from Smith et al. In our solution. However, for more Coulomb material model, we need the modulus of elasticity, we need nu, okay, and we need also the angle of dilation, that is psi, and these values were obtained, E and nu were obtained by different empirical correlations. What I did was I correlated phi to the corrected SPT value, and from SPT value I can find the value of E, and nu also based on the type of soil. I had assumed about 0.3 if I remember correctly. So these values may be different from Smith et al.'s solution, because Smith et al. Have not reported the value of E, nu and psi, angle of dilation. Okay, and these may be the reasons of this small difference between these two analyses. Okay, and I think with this we can conclude that the slope stability analysis of this well analyzed slope by using Salome-Meca and astk gives very realistic result. And also we have seen how we can use astk for running parametric studies using Code-Aster or Salome-Meca. Now what we will see is how to let us see some post-processing of our results that we have got to see how we got these plots, etc., and how we can use Aster-Study for that. Let us see. Okay. So for post-processing, we'll be using our Salome-Meca, and you are all familiar that Salome-Meca has this Paravis module, which is basically a modification of ParaView for reading the made file, our made files. And if you want more sophisticated plots, etc., from the post-processing, then we can use Paravis module. But for quick post-processing, this version of Salome-Meca 2019, also we can use the post-processor that is available along with Aster-Study. Okay, so what we do now is we'll invoke the Aster-Study module in Salome-Meca. And to open our already available RMAD file, what we need to do is, in this data file of the current case, in this screen, in this part of the window, we should select the current case and we can right click. Then I get this menu, set up directories, connect to remote servers, post process the made file results, and assign default file names. Now we will select this. Menu, post process using made results file. Then it gives me a warning that it must be in made format. Our results are already in made format. So we tell it OK, and then we select the result for the SRF of 1.6, which is this one. Then I click open, and it is initializing the post processor for loading the result file. This takes a little bit of time. Now this is my result. Now if I want to see on XY plane, let me do like this, and this is my displacement result, and this was already, if I select something else, you can see that this is in bold, which means that it is being displayed. Okay, now here I have the menu for selection of magnitude and dx and dy component, and if I right click here, I can warp with amplification factor. The auto amplification factor is very large, maybe we can use 50 times x, and then if I press this play button, the whole displacements at various time steps, time instance, will be shown gradually like a movie. So let us press this. So you see how the deformation is changing with time. Here we see the times in seconds. These are my analysis steps, and this is the result of magnitude of displacement, and this is about 40 mm result, right? If I see the dx, then I get this result. I have to play the play button once again, and then we get the result for dx, and this is for SRF equal to 1.65. okay, I can see all other parameters like say sigma NOEU. If I say this, then let us see how the normal stress in x direction is increasing with time, with loading in fact, and this is the final condition of the normal stress in x direction, SIXX, and we may be more interested in SIXY, that is the shear stress. And if I play the play button now, then we can see that this is the result. Okay, and these are sigma NOEU, equivalent nodal stress. All right. Similarly, I can see shear strain FCL no, and this is my EPXX and this is my EPXY. Let me push the play button, and you can see that we have some bands of failure planes developed. Here you see this is my failure plane development from the toe towards higher up, because here the EPXY, that is the shear strain, is maximum as per this scale, 3.7 into 10 to the minus 3, that is the strain. And this side it is negative, that means it is in anti-clockwise direction, because when this is moving down, then this portion stress strain is, of course, this portion, the strain is clockwise, right? Because it is moving like this. It is moving like this. This is my positive direction of x. So it is towards positive direction of x. And in this portion it is towards negative direction of x. So EPXY means it is on x plane in y direction. So this is in negative y direction, okay, and this is in positive y direction, the strain. Positive y direction means if you assume a strain element, material element, let me show you in the other screen. So you see from our usual sign convention of shear stress and shear strain, if the shear stress is such that it tries to rotate the element in clockwise direction, we call that stress and strain as positive. So in positive shear stress, a 2D element will deform like this, and in negative shear stress, a 2D element will deform like this. Now coming back to our strain direction here, you see in this portion the strain is positive because my material is coming downward, okay, and on the y plane the direction is clockwise, right? Clockwise rotation kind of thing. Similarly here there is a slippage in this portion, and this is my negative. So as a reaction, this portion of the soil will be trying to rotate in anti-clockwise direction, okay, and therefore it is negative. So that's how shear strain directions can be interpreted. And you see that this contour shows that there is a shear band formed, failure planes have formed in this zone, okay, at this factor of safety. All right, so this is how we can use post-processing module of Aster-Study for finding the various important quantities. And here, for your information, I am just saying, if you click here, it says save a movie of the current animation. So you can save a movie file for saving the current animation, and you can take a screenshot from here, okay. So like this, the post-processing can be done much more easily um, in this module than ParaView module or ParaVis module. But in some more sophisticated post-processing, like plotting the displacement at a particular time or at a particular section over time, we may need to go for this ParaVis module. Okay. So with this, we come to the end of this presentation, and I hope you enjoyed this tutorial, and you can now take up your own parametric studies for different purposes. Okay, and particularly for slope stability analysis, this parametric study using astk can be easily set up. And if you have liked this video, please press the like button, and if you want to be notified about similar videos in future, then you may subscribe to my channel. Okay, thank you very much.